Welcome to the Deep Learning with Pytorch series. And so far we have covered part one and part two, where we talked about the very basics of neural network and the groundwork of related to neural network. And also we kind of used PyTorch to build certain neural networks. And then we also talked about how to optimize the neural networks, how we can tackle overfitting or underfitting problem in the neural network. And also we talked about how we can speed up the training process of the neural network, right? So slowly we are moving into the part three of this series, which is CNN with PyTorch. CNN is nothing but convolutional neural network, and we are starting with the computer vision part, right, where we will use convolutional neural network to do image classification, and also we will learn the concepts like transfer learning. So with this, let's get started with the part three. And after that, we will have other two parts, which are the sequential modeling and also the graph neural network, right? So slowly we will also talk about those things in very much in detail along with the code examples. So now let's get started with convolutional neural network. Right. So first of all, we already have a multi-layer perceptron, right? So now why do we need a new sort of neural network, what we are calling as convolutional neural network, right? So it's very much essential for you to know why we need a different architecture when we already have MLP, right? So the problem with MLP is that like each of the in MLP we need to have one perceptron for each inputs, right? And so generally we are using a fully connected layer where like the previous layers node are connected to each of the nodes of the next layer, right? So the number of parameters that needs to be maintained while training the neural network is very much large, and that can cause the problem of overfitting, and also a huge number of parameter needs to be maintained while doing the training of neural network for image classification or working with the image, right? So in case for an example, when we have a RGB image, which has a like a shape of 224 cross 224 cross 3. So if you are planning to build a fully connected neural network or a multi-layer perceptron on this image, you need to maintain at least 1.5 million parameters to train the neural network, right? So which is a very big number, and it's very hard to maintain this huge volume of parameters and then train the network, right? So with the help of convolutional neural network, we hope that the number of parameters that we need to maintain and also we need to train, that is very less, right? So another problem is that we cannot pass the image as it is to a multi-layer perceptron, right? So we have to kind of flatten that image. Then we need to pass that image to a fully connected layer, right? So if I talk about like this is my image, and I cannot straight away pass this image to my multi-layer perceptron, right? So we have to kind of flatten this image, and which will be kind of a stretched out vector, which will look like this. And then we can introduce multi-layer perceptron and then do the image classification, right? So this is a problem in case of images, because if you see, if I just picked up this pixel, right? So this pixel which I have here, so this pixel value is kind of have a huge correlation with the surrounding pixels, right? So which what we are also calling as spatial correlation, right? So once we flatten this pixel value, or like the surrounding pixel value like this or this, can become very far away from this pixel, which I have highlighted here, right? So the spatial correlation cannot be maintained if you are like flattening out the image and then using a multi-layer perceptron, right? So that is not the case if we use convolutional neural network or CNN, so which we will talk about very much in detail in next few minutes. But I hope you got an understanding like what are the basic group of problems. One of the problem is like the large number of weights that needs to be maintained while training the neural network for image classification is very big. And another problem is that the spatial correlation if you like flatten the image, then do a multi-layer perceptron, the spatial correlation is kind of destroyed, and the surrounding pixels are, or the nearby two pixels are, uh, does not maintain that spatial correlation, right? So that's why we kind of use the concept of convolutional neural network, where it solves the problem by using a concept called parameter sharing, which also in turn results the less number of parameters to train your neural network, right? So with that, let's try to understand few of the terminologies related to images, because in computer vision or CNN part, we are generally working with images, right? So if I just take an example of this image, so you can see this image is nothing but a matrix of pixel values, right? An image is a matrix of pixel values, nothing apart from this. So it has a matrix where pixel values ranges from 0 to 25, and based on the values of the pixel, your the density of the pixel will be decided, right? And so in case of color images, we generally have three channels, which are like red, green, and blue. So here you can see like this is your red channel, this is your green, and this is your blue channel. So we have three channels which we have in case of color images, and these channels are nothing but two-dimensional matrices stacking on top of each other, right? And which is for each color, we can have one channel, right? And these are nothing but these channels are stacked on top of each other, and that kind of creates the whole image. So in case of color images, if you want to represent a color image using the different channels, we will have three channels, one for red, one for green, and one for blue, and they will be stacked on top of each other, and the each pixel values will range from 0 to 25. Now, in case of grayscale images, you will have just one channel, and here also the values will range from 0 to 25, where 0 indicating the black and 225 indicating the white, right? So you can see like 0 is where the images are like more in the nature of black, and if the values are closer to 255, your uh, pixel values will be closer to white, right? So with this, now let's talk about the different building blocks of convolutional neural network, right? So the first building block is convolutional operator, right? So in case of convolutional operator, we have a working principle where the nearby pixels are strongly related to than the pixels which are distant ones, right? So we already talked about the spatial correlation. So using this convolutional operator, we will try to maintain that spatial correlation, and it will work on this working principle that the nearby pixels are more strongly related than the distant ones, right? And with that, let's see what we generally do in case of convolutional operator, right? We run through a filter which from top left to bottom right, and this pixel values or this filter we also call as kernel, right? And each of these kernels will have different purposes. Like one can detect edges in the image, and one can detect, like if you are doing a human image classification, then one can detect edges, one can detect eyes, or if you are doing like a classifying a car, then some of the kernels can be responsible for detecting the wheels in that image, right? So as you can see in the in this animation, that pixel filter which is colored in yellow, that is being run through from top left to bottom right, right? And we are getting a corresponding value at the output layer after running through this filter from top left to bottom right, right? Now this operations which are happening, this mathematical operation is nothing but a element wise multiplication and then summation, right? So if I just take this example, I have this range of pixel values, and where we have values like 301, 262, and 241. And the filter or the kernel which we are running, this has the corresponding values like -1, 01, -2, 02, and -1, 01, right? So as I mentioned, the mathematical operation is nothing but element wise multiplication, and then we are doing a summation. So this -1 will be multiplied with 3, and then this 0 will be multiplied with this 0, and this 1 will be multiplied by this 1. So you can see these are the operations which are going on, the element wise multiplication, and then we will do the sum to get a single value, right? So that is single value will be represented here, which is nothing but -3, right? So this is what we generally do in case of a convolutional operator. We run through a filter from top left to bottom right, and we kind of do this mathematical operation, which is nothing but element wise multiplication, then summation to get a final output, right? So here you will see like I'm running a 3 cross 3 filter, right? So this 3 cross 3 filter will have parameters which are like 9, and this parameter values, like the values which are assigned here, right? -101, -202, and -101. This will be learned during back propagation of the neural network or the convolutional neural network, right? So we don't need to bother about what would be the values of this kernel. So that will be decided during the back propagation, right? And the benefit what we get is it reduces the number of weights the network needs to learn compared to the multi-layer perceptron. So we have seen that uh, for the given example, there was around like 1.5 million parameter values which we need to maintain, and also we need to train. But in case of convolutional operator, we can see like with minimum value of 9, we can like pick up certain features in that are present in the image, and we can do this convolutional operation, right? Now moving on to like what these filters can do, right? So based on the values of this filter, it can do different type of task, right? So one, if the values are like this, so it can be a identity operation, right? So it can just mm, give you back the image as it is, right? Now there are certain other filters are there, like edge detection. So one can be like vertical edge detection, one can be like horizontal edge detection, and also there can be other edge detections which are like this, right? And with that we can kind of capture the pattern in the image, and based on that we can do certain classification on top of that image. So there are other filters which are like this values will kind of sharpen the image, and some will like normalize the image, and some will also can do uh, the Gaussian blur of the image, right? So based on the based on the values of the filter or the kernel, it can do different type of task on top of your images, right? So now, as I mentioned, like we will run through the filter from top to bottom, and we can have different type of stride, right? So first of all, like if I have this type of image and I have this 3 cross 3 kernel or filter, so at first it will be placed here in this way, and after that it can have different type of stride. So if I take stride equals to 1, which is nothing but s equals to 1, then after doing this operation, then it can move to this position, right? So when I am mentioning the stride equals to 1, right? So now if my stride equals to 2, it can move to starting from this position to, like with stride equals to 1, the window or the filter move from this position to this position, right? With stride equals to 2, it can move to in this position, right? And the next step will be starting from here, right? So here with this you can see like with a stride equals to 2, your next run through of the filter will move 2 steps and it will be placed here. And similarly, we can have the same operation in the while it is moving downwards also with stride equals to 1. The next time it will be placed here. And if the stride equals to 2, this is stride equals to 1, right? And if you have stride equals to 2, and the next time the filter will start from this position and it will be placed here to do the operation, right? So it is how you are convoluting the filter through the image, right? So and it will take like the stride equals to 1 or 2 will have both the impacts in the horizontal and vertical direction separately, right? So I hope you get an understanding with that, like what will happen if you do a stride equals to 1 and a stride equals to 2, and based on that your next destination of the kernel of the filter will be decided, and that will be placed inside the image, right? So this is another building block of CNN where we kind of we can do a strided convolution with the values of 1 or 2, and we can get an output pixel values for the input image, right? Now, as I was mentioning, right, so based on the filter or the kernel values, we can get different types of output and different types of operations that the kernel can do. So similarly, if you build a deep neural network, a deep convolutional neural network, so at the starting, your the filters can work as like it will pick up certain low level features, like it can detects the number of edges, and in the later layers it can also act as a mid-level feature detection, right, which can detect like nose and eyes, so those type of uh, the features it can extract from the image, right? And later on it can detect, you just hope that with this intermediate feature extraction, and in the end it can detect the high level features which are available in the image, and it can do a image classification, like it will tell you that this is nothing but an image of human, right? So with different layers or stacking different kernels or filters, we can detect starting from low level features to a high level feature, which in the end can detect the what is being present in the full image, right? And all this convolution operations are nothing but a feature detectors, right? So it will detect what are the features that are available in the image, and later on it will detect like the high level features that are available in the image, right? So so far we were talking about like how the convolutional operation works in case of grayscale images. In case of color images, in color images we have three channels like this, and we can also do convolutional operation on this color images also, right? So here the filter channels will needs to be matched with the number of channels in the input layer. So here we can see like we have three channels or three filters present here. Actually, this is a one filter and it has three channels, right? So here this three, the number of channels needs to be maintained, which needs to be same as the number of channels that are present here. So here also three, here also the your number of channels in the filter should match the number of channels that is being present in the input images, right? So here we can see like each of this is 3 cross 3. So 3 cross 3 filters, and we have total 3 filters. So there will be 27 parameters that needs to learn during the back propagation, right? So with that, let's move into the next slide where we will talk about like we can stack multiple filters also on top of each other when we are doing the convolution operation in terms of color images, right? So we have this color image which is like 6 cross 6 cross 3, and we have two filters, right? So filter one will have three channels, and here also this will have three channels, and then we will get an output of 4 cross 4 two images, and in the end we can get uh, image which will be like the output will be stacked on top of each other, and the shape will be like 4 cross 4 cross 2, right? So these are the operations which we can do in case of color images using a convolutional operation, and this filter or kernel values will be learned during the backpropagation step, right? So let's get talk about padding. So as we have seen in the convolutional operation, so we run through a filter from top to bottom. And if you look closely this image, you will see like the edges, like the edge pixel values, which are nothing like this pixel, right? Or this pixels are when we are running through a filter, this will be only visited once, right? So this pixel values can have like key feature values which are there in the image, but as the kernel is touching only this pixel values once, can so we can lose out some important informations which are present in this like edge cases, right? Or the edge pixel values. So what we can do is we can introduce the concept of padding, where we can like introduce zero padding, where we can pad the image with zeros. So here you can see, like here the zeros are being padded surrounding the whole image. So now if I do a convolutional operation, so this edge pixels, right, which are like this pixels, so that will be also visited multiple times when we are doing the convolutional operation, right? But if you don't do this padding, so here you can, in this case only, you will see like this pixel value will be only visited once uh, by the filter or the kernel, right? So which can lead to losing out information which are very important for that, which are present at the edges of the images, right? So just to avoid that, we can pad the image with zero padding, and that will kind of keep these important informations which are available at the edges, and then it can do the convolutional operation. So the benefits here, like introducing zero padding around the edges, will ensure that the information from the edges are also collected during the convolutional operation, right? So with the help of zero padding, we can also capture the important informations which are present at the edges of the image. Now, moving to other components of convolutional neural network, or the building blocks of convolutional neural network. So far we are doing kind of we are running through a filter and we are doing the convolutional operation, right? So this convolutional operations are linear in nature, and we can introduce non-linearity by introducing the ReLU as an activation function, right? So this ReLU can also help us to remove negative values from the input, right? So in some of the cases, we need to remove certain negative values which are present in the image, and ReLU can also help us to do that, apart from introducing the nonlinearity to the learning process, right? So here we can see the example, like black values are negative values and white are positive values. So if you want to just extract the white values or the non-negative values, we can introduce a ReLU, and it can like pick up those only the non-negative values as an output of that image, right? And also ReLU can also help us to tackle the vanishing gradient problem, which we have discussed in the earlier videos also, right? And next, the other concept or the other building blocks of CNN is pooling, right? So as we have seen, like we are running through the filters, and here it is kind of creating a new set of images, a new set of images with a new set of number of channels, and that can also increase the number of parameters or the size of the image. So how pooling can help us? It can help us to reduce the size of the feature map by keeping only the key features, right? So by reducing the height and width of the feature map, which will also reduce the chances of overfitting, and also the dimensions of this whole process will be kind of manageable, right? So there can be two types of pooling, which is like max pooling and average pooling. So just to take and give you an example, here we have this input image, which is this image, and here we are doing max pooling. We are running through a filter of 2 cross 2, and we are running on a stride of 2. So at first your filter will be placed here, and we are doing a max pooling, so it will pick up only the max value out of this. So this 6 will be placed here, and it will be present in the output. Then it will move to 2 strides, and here it will also see what are my maximum value. So this 8 is the maximum value, and that 8 will be picked up here. Similarly, it can move here and then here, and it can pick up the key features, only the key features out of this image, right? So with that, we will hope that we are only keeping the key features, and we are throwing out the redundant informations which are available in the input image, and we are also reducing the number of parameters or the dimensions in a more manageable numbers, right? And in case of average pooling, here we are just picking up the max value, right? In case of max pooling. So in case of average pooling, we will calculate the average of these four numbers, and that will be populated here, right? Okay. So that is the concept of pooling, where we can do two types of pooling, max pooling and average pooling. And here no parameters are involved, right? We are just running a filter, a 2x2 filter across the image, and those filters does not have any values which it contains, so there is no parameters to learn, right? So that is kind of the beauty of pooling, right? We are not introducing new parameters, but we are reducing the number of parameters that we need to manage in the learning process, right? So with all these building blocks, the last building block is a fully connected layer, right? So generally what we generally do is we have our input image, which is this is our input image. Then we do a convolutional operation, and then we do a pooling layer to reduce the number of size of the parameters. Like here, if you see, like this image was like 28 cross 28 cross 6, and here the 28 cross 28 got reduced to 14 cross 14, right? Then again, we use a convolutional layer with like filter size of 5 and a stride of 1, and we get this, sorry, we get this output shape. Then again, we can use a pooling layer. So it's like an two back-to-back layers, right? One is convolutional layer, then a pooling layer, then again a convolutional layer, and then again a pooling layer. So with that, we will get an finally we will get a image, and that we will flatten out and pass through a fully connected layer, right? So and with the help of fully connected layer, we can in the end we can use a softmax to do a classification of that image, right? So this fully connected layer will help us to do the classification on top of the image. So as I was mentioning, like we cannot use a fully connected layer on top of an image due to the constraint of like the two constraints, right? Where if you use a multi-layer perceptron, we have to maintain a lot of parameters. And also if we use directly a fully connected layer on top of an image, we can lose the spatial correlation, right? So with this like layer one and layer two, where we are doing like convolutional operation twice followed by a pooling operation, we hope that it will kind of capture the spatial correlation, and then we will kind of flatten out the image, and we will use certain fully connected layers, and then we use a softmax to do the image classification, right? So these are kind of the building blocks of your full convolutional neural network. We have our input image, then we can do a convolutional operation, then we can introduce a ReLU to introduce the non-linearity in the learning process. After that, we can add in max pooling layer to kind of reduce the number of features, and then we can stack another convolutional pooling layer, and in the end we can use a fully connected layer to do the classification, right? Okay, now let's talk about the last part of this video, which is like the understanding of the dimensions, right? So as I was mentioning, we have an input image of like, say for an example, 32 cross 32 cross 3. So here, this is like height, width, and this 3 is nothing but the number of channels, right? So the mathematical operations that you need to understand is like we have our input image, which is like n cross n cross c. So this n cross n, we are mentioning this is like height, and this is width, and this is the number of channels which we are denoting as NC, right? And we are running a filter on top of this. Here, the filter size is like f cross f. So here we can see the filter size is 5, right? So we are running a 5 cross 5 filter, and here the number of channels should always match the number of channels that is present in the input image, right? Then we are using padding, and also we are using a stride, right? So the output, how it will be calculated is this formula: n plus 2p minus f divided by s plus 1, right? So similarly, this is for height, this is for width, and the number of filters that we are using, that will be used as a channel for this output. So if I take this example, like which is my input image is 32 cross 32 cross 3, and my filter was like 5 cross 5 cross 3. This 3 and this 3 should match, which is the number of channels in the input image and the filter. And then we are using and so here there is no mention of padding, so I will keep padding as 0. So we are doing a 0 padding, and also we are using a stride of 1. Right now, if I plug in these values, so my n is equals to 32 here, and padding equals to 0, then we will subtract the value of size of the filter. Then we will divide with the value of stride, which is 1. Right, so this value will come as like 32 minus 5 is 27, and we also have a plus 1 here. Right, so this 27 plus 1 will come as 28. So similarly, we will calculate the values of width, which will also give us the same value, 28. And here you can see the output is 6. Right, so we are using 6 filters here. Right, so here NC dash is nothing but 6. So we will get an output of 28 cross 28 cross 6. Right, so that's what we are also getting here. So you can like do the math for the later layers and see how the operations are going. So in case of pooling layer, it will just reduce the size by 2. Right, so your 28 cross 6 will become 14 cross 14 cross 6. Right, so I hope you got an understanding of this whole working of convolutional neural network, and in the next video we will try to do a hands-on coding part, and we will try to do image classification using Pytorch and convolutional neural network. Right, so yeah, thank you all, thanks for your time. See you in the next video.